Okay, in order to understand the concept of cells, polarity, and also load or resistance connected in series and parallel, the effect, how it affects current. We're going to use this question to get an understanding on the concept. So this question says, two similar cells are used to light two similar lamps as illustrated in the diagrams above. In which of the circuit diagrams are the lamps brightest? So now they are telling us two cells. This is cell number one. The small this thing represent the negative, the tall one represent positive. So this for diagram P. So these are two cells, and we are told that those two cells are similar. That means they generate the same EMF or voltage. And then we also told that the lamps are similar. So what we notice here is we see a forward connection here. That's the positive of this one to the negative of the next battery, from the negative to the positive. So this is this kind of a forward, should I say biasing? I know biasing is for analyzing transistors. So this is kind of a right connection, which means the voltage add up. So assuming the voltage on the first cell was is 1 volt, and the voltage on the second cell is 1 volt. This sort of arrangement where the positive of this one is connected to the negative, like that, a forward arrangement, the equivalent voltage or EMF will be what? 2 volts. That's the first thing we have to know. uh So then you look at the connection of the lamps. These lamps are connected in series, and lamps can be seen as a load, and load is represented with resistance. For this level, we use resistance. In higher level, we have things like impedance or reluctance, but for this level, we see it as a resistance. So now these are resistance connected in what? Series. Now, without talking much, if it was just me that they asked this question, I was in exam condition, and they asked which of it would be the brightest. The correct answer would be option Q. The correct answer would be option Q. And how do I know that? I know that because when you connect resistors or resistance in parallel, the equivalent resistance is reduced. But when you connect resistance in series, the equivalent resistance is increased. It's very big. It add up. But in parallel connection, it reduces when you take the effective resistance. So that means there will be less opposition to the flow of current from this cell. And this, since there's less opposition to the current from this cell will be higher. The current from this cell will be higher, and when that current comes in, it will be shared equally into two. So these lamps will be brighter. But you see this one, when you add up the resistance becomes very high, and because of that, the current that will be drawn from this cell here will be low, which will make it not to be very bright. Then you come to the third diagram R. The You see the way these cells are connected in a reverse manner. You see positive terminal, negative is connected to negative. So it's not in a forward, or it's not in a forward arrangement. So that means the EMF or the voltage will cancel out. If the batteries or cells were connected, this positive negative connected to another positive negative, they will add up. If this was 2 volts and this was 2 volts or 1 volt, equivalent EMF will be summation of the two. But when they are connected in reverse, the negative of this one connected to the negative of this one, it will be a difference. So depending on the value, if this one was 2 volts and this one was 1 volt, that will be the difference between the two. The equivalent EMF or the equivalent voltage will now be 2 minus 1, which will be 1 volt. But in this case, we are told that the cells are the same. So being the same, they will cancel out. That will be 1 minus 1, 0. So they won't be generation. The EMF will not be generated here. Voltage will not be generated here. And since there's no voltage, there won't be current. So no need to even consider whether it's now series or parallel. Same thing goes here. The cell is connected in reverse manner, so they will cancel out. So no voltage and current is being generated. So here will not go, the lamp will not lamp at all. S and R, nothing goes there. It will be totally off. But P and Q will be on. But however, Q will be very bright because the equivalent resistance to the current drawn is low. Now, let me prove it by solving. So, assuming each of these cell is 1 volt, 1 volt, and equivalent EMF is now 2 volts, and then these lamps, we assume they are 1 ohms, 1 ohm, each of these lamp 1 ohm. So let's analyze that of P and C. So we will first calculate the equivalent current, I subscript P. Equivalent current I subscript P will be what? V, that's the EMF or the voltage, divided by the equivalent resistance, the total resistance. And the voltage in this case, the equivalent voltage is 2, divided by equivalent resistance will be 1 plus 1. You know, since it's series, you add it, which is still 2. So the current I subscript P will be what? 1 amp. So you see that the current that will be drawn from this cell will be what? 1 amp. And you remember in series connection, the same current passes through individual component or device on that line. So the same current in the first lamp will still pass through the second lamp since they are in series. But in parallel, the currents always divide themselves. The currents always divide themselves. So we come to parallel connection to do the same analysis to see the current flow. Now, in this parallel connection, I subscript Q, that's the current drawn. This place is I subscript Q. The current that will be drawn from this cell will be equals to V divided by the equivalent resistance. And V in this case will still be 2 since it's a forward connection. 2 divided by. Now, resistance in parallel is since there are two resistance, to analyze them, that will be 1 times 1 divided by 1 plus 1. So this will be 2 divided by 1 divided by 2. That means 2 divided by a half. If you do this correctly, division of fractions, this will be 2 times 2. 2 times 2 to give you 4, 4 amps. Now, you know this 1 over 2 in the bottom here represents the equivalent resistance. So you see in parallel connection, the resistance has been reduced. The resistance on this one was 2, but the resistance on the parallel connection is half. So you see that the equivalent resistance has been halved. So less resistance means increase in current. Less resistance means increase in current, and of course you can see it here. Now the equivalent current, total current run from the cell is now 4 amps. But for this other one that was in series, the total current drawn is what? 1 amp, which is very small. And this one, the total current drawn is what? 4 amp. But it's not this 4 amp that will enter this lamp, that will enter each of this lamp. You know, this is a parallel connection. When this current 4 amps reaches here, this junction, it will divide into 2 based on the value of the resistances. But since the resistances are the same, it will divide equally. So you have 2 amps here and you have 2 amps here. So you see that the current that will be driving this first diagram will be 1 amp, while the current that will be driving this second diagram, each of the bulbs in this second diagram will be 2 amps. So a greater current means greater power, so the illumination will be greater there. So option Q is the answer, and Q is which option? Q is option B. So the second diagram will give you the brightest. Will give you the brightest. So subscribe to my channel and give a like, as this is a sole way of supporting the ministry. And also, if you want a one-on-one tutoring online, you can join my WhatsApp group via the link in the description. Then we discuss, and then we you can learn directly from me. Thank you.